Hi everyone, this is Tom with some tips on this problem. So in this problem we're talking about the BJT as an inverter. Now this is a circuit that you can use to start building digital logic if you like. So the way it works is there's this input voltage here. So the way this works is that there's this input voltage here that controls this output voltage here between the collector and the emitter. So let's look at our equivalent circuit of the BJT. We'll see that the main device here is a current-controlled current source. So this current IB is multiplied by this factor 200, which is sometimes called the beta of the transistor. It's really the current gain. And that controls the collector current entering in the transistor. So a small current going into the BJT causes a large current to flow from the collector to the emitter. And that current is supplied by this DC voltage source here. So IC actually also goes through this branch and causes a voltage drop across this resistor. So Vout is going to be this 5 volts minus the collector current times the 1K resistor. 5 volts minus the voltage drop. So if we were to draw on these two axes, Vin and Vout, what would happen? So at some point, the transistor will be off. So why is that? Well, it's because the base emitter junction can be modeled as a diode. You can model it as a diode. So I'll go ahead and draw the diode in here. And this diode only turns on when we're above the forward voltage of the diode, which in this case happens to be 0.7 volts. So no current will be able to enter the BJT if we're below a certain threshold. So if IB is 0, then the output current is 0, and we don't get any voltage drop across the transistor. So we're going to be up here at 5 volts. But at some point, now I may have spoiled the problem a little bit, but at some point this transistor will now turn on. This diode here between the base and the emitter will turn on, and this becomes your equivalent circuit model. There's this DC voltage drop due to the forward voltage of the diode. Okay, so now we have a non-zero voltage drop across the resistor RB, and that causes a current to flow, the current IB to flow into the transistor. So now that you know what IB is, you can calculate what IC is and finally get what the voltage at the output is. Now, in general, as this voltage increases, or as this voltage at the input increases, IB increases, IC then increases, and we get a larger voltage drop at the output. So actually, as Vin increases, Vout decreases. So the problem first starts by asking what happens when Vin is 1 volt. So it walks you through the calculations of figuring out what Vout is, figuring out eventually what Vout is. Vout at Vin equals 1 volt. The question then challenges you to work your way backwards and consider when this graph hits 0, right? At some point, there's going to be so much current flowing into here, so much of a voltage drop across this resistor that will hit 0. And we can't go below 0 because we only have this single-sided voltage supply. So for the rest of that graph, we're at 0 volts. So the second part of the problem asks you to work backwards and figure out what this Vn is. What this Vn that causes the transistor to essentially completely drop that 5 volts across this resistor. So in this case, the bare minimum is that the voltage drop across this resistor, IC times 1K, equals 5 volts. In this case, the output voltage will be 0. So that's what the second half of the problem is getting at. So hopefully you can see how this is an inverter. For low Vin, we have high Vout, and for high Vin, we have low Vout. It's as if we're inverting the level of the input voltage. However, there is this transition region. Now, this transition region can be useful depending on your application, but if you wanted to use this circuit as a digital logic circuit, then it's important for you to stay within these well-defined regions. So hopefully that gives you a little bit of insight into the problem and what we're really asking for, and clarify some things if you were getting stuck on it. Thanks.